Thanks. So yeah, this is going to be about Disco, which is normally thought of as MapReduce implementation. Things have changed a little, so I'll be talking about what's changed. And the idea is that it's kind of time to move on beyond MapReduce and how Disco is trying to do that. So Disco is a big data platform that does MapReduce, so I'll just kind of set up the context, what we mean by that. Well, Disco has been presented at Erlang Factory a couple of times, but in case for people who aren't aware of Disco, I'll just go over the architecture of Disco at a very high level. I won't spend too much time on that, but please feel free to ask questions. And then I'll go into what is going to come in the next release of Disco. It's what we call the pipeline model. I'll kind of describe why, what motivated the pipeline model, what it is, and what kind of things it solves, and also what it doesn't solve and what are the limitations of it. And just conclude with the Disco roadmap. Big data has got a very simple definition in my opinion. It's just basically data that doesn't fit in one machine. It doesn't fit in one machine's RAM. It doesn't fit in one machine's disk. You need to store data or analyze data using multiple machines. And the simplest way of doing that was what Google came up with almost a decade ago now. You have chunks of data distributed in a cluster. You analyze pieces of data in parallel. You call that the map phase. You get the intermediate data together in one place, and you compute the final result in a step called reduce. And you use a cluster of machines to do that. And this is what it kind of looks like. You have parallel maps that analyze pieces of data, and then you have reduces that generate the final output. And there's a hidden step there called shuffle, which is kind of usually ignored unless you get under the hood of MapReduce, and that's where a lot of problems lie. A lot of problems lie here in Disco as well, and in fact, that's one of the reasons why we came up with the shuffle, with the pipeline model. I'll be getting back to that. So the origins of Disco, our host was one of the the originator, and it's now just over 5 years old now, so it's been around for a while. And this is what the architecture looks like. You have a master node that kind of controls the whole MapReduce game, and you have compute nodes that run Erlang node that are basically worker nodes on which computation is done. You have a client that interacts with the cluster via the master. There's a simple JSON HTTP protocol. And the user code, the code on through which you actually analyze data is the green block there that runs on the compute nodes. So what happens is when you submit a job, your client takes your code, compresses it into a zip file, submits it to the master. The master sends it to the compute nodes, and the compute nodes unpack the zip file into a worker directory and launch your designated executable in the zip file. That executable runs, it becomes the green block there. Your executable is linked against a library that talks to Disco. That's the small blue circle there. It implements something called the Disco Worker Protocol. It's a very simple protocol. It can be implemented in any language. In fact, you can make any language a first-class citizen of Disco. So we have Python, which is the supported one, and we also have an OCaml implementation of Disco. Your user code accesses the data over HTTP or from the local file system. Usually it happens over the local file system. So the idea is the code runs local to where the data is. One thing to note is that your user code accesses the data directly. It doesn't go, the access to the data doesn't go through the Disco architecture. That's almost quite right, except in one place. I'll come back to that. That's one of the things we fix in the pipeline model. This is the worker protocol. The details are not important. It's just a simple protocol. It tells your code what task it's running, where to get its inputs, and when you generate outputs, where you tell Disco where you've put your outputs, and then you say you're done, or you say you have some error. I mean, it's a very simple control protocol. There's no bulk data going through this. One of the things that you need to provide with any big data system is a place to store data, and Disco comes with its own distributed.
Can you take a look at your microphone here? We're having issues with the live stream. Where is it plugged in? Just need that part.
Okay.
Check, 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 check. Okay, looks like it's okay here.
Should I go on? Okay. So the distributed file system that comes with Disco has got a very simple implementation. It's fairly similar to the compute infrastructure. There's a master node that coordinates a bunch of storage nodes which have locally attached storage. The client interacts with the master to get metadata about where the data is located, and it interacts with the bulk data directly over HTTP to the storage nodes. No bulk data goes through the master. So this is what the layout of your data looks like in Disco. It's not a POSIX file system. It's not tree structured. There are no concepts of directories. It's a tag structured system. And so tags can point to bulk data which is replicated for fault tolerance. And you can have multiple tags pointing to the same bulk data, and you can have tags pointing to tags, so you can have a hierarchical structure that way. So it becomes a directed acyclic graph. It's not a tree-structured POSIX-style file system. It kind of provides a lot of flexibility in addressing your data. This is what the metadata looks like in the file system. It's basically a collection of where your data is located. It's very simple. It points to the replicated blobs where they sit in the file system. It also points to other tags that are addressed by this tag. There are a bunch of attributes that you can set in your metadata, key value pairs that you can add additional metadata in addition to the name. And there are also simple access control tokens. You can have a read token and a write token, so you can control who can access your data. You need to have the right token to do the right, to perform the corresponding operation on the metadata. This is the only mutable data in the system. The bulk data there is immutable. Once you push data into the file system, it stays as it is. It cannot be modified unless you delete it. The tags, the green blobs there are the only mutable state in the file system. So you can add bulk data into a tag. You can remove bulk data from a tag, and you can delete a tag. You can create a tag. So that's where the mutation happens. It enormously simplifies the implementation of the file system. This is what Disco looks like in terms of code size. It's extremely small. Here are the lines of code for Java. It's an order of magnitude smaller. A few thousand lines of code of 8,000 lines of code in the MapReduce compute segment. This is for the development branch. The last release are actually a little smaller than this, but the next version of Disco is what these numbers refer to. It's around 4.600 lines of code in 4.6,000 lines of code in the distributed file system. And the Python library is 3,000 lines. OCaml library is 1,700 lines. And of course, one thing that's missing in this are the external dependencies of Disco. So these look very small, and you kind of don't, you should be suspicious of very small numbers like this. Of course, what's missing is the external dependencies of Disco. So it depends on an external HTTP library, which is MochiWeb, which is in fact, almost the size of all of the rest of Disco. It's 12,000 lines. There's a logging library, the logger, which is around 4.3 thousand lines, and of course the standard libraries of Erlang and Python. Okay, so let's get back to what's new in Disco. Any questions on Disco so far? So this is the MapReduce flow graph. And the motivation for the new stuff that I'm going to talk about is a bug in the scheduler. It doesn't backtrack. So what happens is that currently, if you run your maps, you do your shuffle, and you start running your reduces. And by the time you start running your reduces, one of the nodes on which the map ran goes down. And your reduce cannot access, so your reduce cannot access this data because the node on which this data was hosted goes down. What Disco cannot do right now is rerun that map somewhere else in the cluster. So it cannot backtrack and fix missing data earlier in the task graph. So that's a bug that kind of motivated what I'm going to talk about. Another kind of issue that is that currently exists in the stable release of Disco is that the shuffle step is actually implemented in the master, which kind of is not quite nice because this is one place where bulk user data actually goes through Erlang. And we kind of like to think of Erlang as a control, as the control plane, and no bulk data goes through the Erlang portion of Disco, but this is one place where actually it does go, and that's not quite nice. In fact, this is one of the reasons why the backtracking scheduler is kind of complicated to implement. So in trying to address these two issues, we took a look at what's happening here, and we rethought the whole MapReduce idea. And there's certain problems with the whole MapReduce idea, which is that the job computation is done in 3 fixed stages. These are the stages. There's a map stage, there's hidden shuffle stage, and there's a reduce stage, and it's kind of inflexible. And you have to implement all your computation in this limited framework. It's kind of constricting. Another problem with this, the conventional presentation of MapReduce is it's tied to key value pairs, and maybe you cannot express your computation always in terms of key value pairs. This is actually fixed in Disco already. If you look at the protocol, the job protocol, what you get in your user code, actually what it gets is input and output. There's no notion of key value pairs. That's actually implemented in the worker library. It's a library implementation. It's not core to the Disco Erlang portion. And another limitation of MapReduce is that there is no inter-task optimization of network resources. Now, you're usually, you run into network resource issues with very large jobs, and as machine learning people who are data analysts, you normally don't think of network resource consumption, but once you actually start getting once you become a power user of these systems, you start running into network resource issues, and it would be nice to provide the users hooks in which they can address problems of network resource consumption. So I'll get into this in a little more detail. So what happens once your MapReduce task flow graph actually runs in a cluster, you will have some tasks that actually run on the same node. So that's this gray box here. So you have 3 maps that ran on the same physical or virtual node. They produce outputs that are partitions, and those partitions are sent to the reduce stages. Now, what's actually happening is that all these partitions are sitting on the same physical node, but your reduce is running somewhere else on some other physical node in the cluster, and all of them have to be shipped across the network. And that's one of the reasons Shuffle is kind of expensive in terms of network resources. All these files that are sitting on the same node have to be shipped across the network. And what would be nice is that there might be a way of moving a portion of this reduce into this node to access this data locally at the node instead of sending it across the network. Notice that this is different from what is called combine in MapReduce. Sometimes you come across this local combiner. Combiner runs in the context of a single task. What we are talking of is combining across tasks that ran on the same node. So it's slightly different from the concept of a combine. You could think of it as a node local combine instead of a task local combine. So this is what you could do is, what would be nice is if a portion of these tasks were pulled into a physical node so that they could access the output files of this previous stage locally to that node, compress, generate a summary of all these intermediate data, and send the smaller, the assumption is the summary is smaller than the input data, and send those smaller compressed summaries across the network. And so what's actually happening here, if you look at it, is you have one stage of tasks that generate outputs that become the inputs for another, the subsequent stage of tasks. And what's actually happening is you're kind of routing inputs into, you're grouping outputs as inputs for the next stage. And there are various ways in which you can do this kind of grouping. So what's actually happening here, if you think about it, is there's a grouping by label. So the color is the label here in the context of a single node. So each task there, each colored task there is actually collecting all the, is grouping all the outputs by the label of that output in the context of a single node. So you could kind of call it as a group by label per node. That's one possible grouping you could do. Another very simple grouping you could do is just group all the outputs of the previous task that ran on a single node into one task. Process all this intermediate data and then construct whatever output data you have, and then send it out of the node. So this is another possible output grouping. So what's actually, I mean, if you step back, what's actually happening is you have stages of tasks and you have grouping operations performed inside. So this is effectively, you've arrived at the pipeline model. You have pipeline stages of tasks. A pipeline is a sequence of stages, and each stage performs some grouping of its of the previous stage's outputs and runs some task, some computation on those inputs. So that's basically the pipeline model that Disco will have in the next release. And so the question is, okay, if it sounds very nice, but can you actually implement what you could do before? Actually, I'll get back to that. So here are some other possible grouping options that you can do. You could have what we call a split, which is for each possible input, you run one task. Okay, so there is no grouping effectively. It's just each input has some task. That's called the split. So that's typically performed in the map phase. You could have a group label kind of grouping, which kind of groups all outputs across the whole cluster, depending on what label the output has. So there's no node locality in the group label option. The grouping is done across the whole cluster. And similarly, a group all grouping just consumes all the outputs of the previous stage across the whole cluster. So again, there's no concept of node locality there. So yes, so once you have this pipeline model, you can express MapReduce as a pipeline, since it's the pipeline model is a strict generalization of MapReduce. So MapReduce can be easily expressed in terms of the pipeline model as map stage, which performs a split grouping. So there is a map per input chunk. There's one map task per single input. And this is the case across the whole cluster. There's no node locality there. And the reduce stage groups by label all the intermediate output files and performs a reduce. So you can express MapReduce in terms of the pipeline model, but the pipeline model is more flexible. So what does the pipeline model do? It fixes existing issues in Disco. Using the pipeline model, it's easy to think of a general backtracking scheduler. It can backtrack not just across the map shuffle reduce phases, it can backtrack across a whole sequence of stages. Also, by exposing the shuffle stage into user code, you actually avoid any bulk data going through the Erlang portion of Disco. So both of these issues are fixed in this pipeline model. In addition, what it provides is a fairly flexible compute model. You're not restricted to expressing your computation in just MapReduce phases with a hidden shuffle stage which you really don't have access to. This allows you to express your computation in a whole bunch of stages. And it allows you to perform node local optimizations in case you want to. So in case you're interested in reducing the amount of data that's shipped across the network and cause a whole bunch of problems like TCP incast and stuff like that, what you could do is you could have explicit node local stages that compress all the data on a single node before it's shipped across the network. So it's a fairly flexible compute model. Also, it's a pretty simple or conservative extension to MapReduce. It's a linear stage, linear sequence of tasks. It's not an arbitrary graph data flow, which like Dryad is pretty interesting data flow programming, big data framework that came out of Microsoft. It's pretty general. The problem is that generality, it allows you to express arbitrary data flows, graph structured data flows, but in order to express your graph, you need a DSL. It's kind of complicated. Not only are you writing your data processing code, you're also writing code that computes your graph or expresses your graph. So here it's very simple, it's very declarative. You have a sequence of stages. There's no need for a DSL to express your graph. And it's probably a more flexible platform for higher level tools that are normally built on top of MapReduce, like Pig, Flume Java, which take your computation and then run a whole bunch of MapReduce jobs in the background and to basically express your high-level computation. Now, this pipeline has limitations because it is intentionally not very general right now. There are no forks and joins in the data flow. So you could kind of implement a limited amount of forks and joins, but I won't go into them. You can kind of use labels to implement some restricted forks and joins, but it still has some limitations. It's not general forks and joins. And also, there's no iteration or recursion. So it's a linear sequence. Currently, it doesn't allow you to iterate, go back into some previous stage and iterate or recurse. And usually, you do require things like that for machine learning computations where you have some convergence criteria and you keep iterating until you're algorithm or your computation converges to some result. So this could, this could be implemented in future iterations of the pipeline model, but right now it's doesn't exist. So now that we have this new pipeline model, we don't have any map or reduce tasks. So how exactly do you program this? So you need a new API. The previous version of Disco you just had to provide a map function and a reduce function, and that's all you did. And everything else was taken care of for you. Here you need a new API for your computation. You need to provide a process function that processes your data in a certain stage. That process function iterates over the data, so you're given an iterator over the input, and you just consume the data. And so it is different from the previous API where you provided a map function and data was pushed into it, either map or reduce. You had key value pairs pushed into your function. Here you pull it using an iterator. Also, there's simpler handling of processing state. You have init and done hooks. So you can specify an init function that generates, that creates your initial state for your function. It gets passed into your process function, and it returns, the process function returns an updated state. It's kind of a fairly functional style API. And the done hook gets called with the final state, and you can do whatever you like. You can generate your final output. And there's also an input hook that allows you to control the order in which you iterate over the inputs. In map and reduce, you really don't have access to the, you could consume several inputs, but you really don't know how many inputs you're actually consuming. The input hook allows you to actually control the iteration order over your various inputs. So this is the so this kind of summarizes what's new in Disco, in the next version of Disco. So there's a backtracking job coordinator. You have a pipeline model, which is a more flexible compute model. You have an alternative task API, which allows you to get a little more control, a little more visibility into what your data is. And you have the existing MapReduce API implemented on top of this infrastructure, on top of the pipeline infrastructure. So almost all your existing Disco jobs will run without modification on the next version of Disco. There are a few corner cases which will not work. That's if you use some scheduler options, or you kind of control the number of reduces. There are a few cases where they won't work without modification, but almost all your conventional MapReduce jobs in Disco will run without modification. Beyond 0.5, we are interested in evolving this pipeline model depending on how people use it, because it's kind of new. We haven't used it extensively ourselves, so users, once they start using it, they will probably ask for features and modifications, and it'll be a evolution for the model. Also, one area that we're kind of interested in evolving Disco is getting the scheduler a little smarter about the network topology. Right now, it has a very simple idea of how your cluster is laid out. In typical physical clusters, you have servers racked in racks, and the network distance between servers in a rack is different from servers across racks. So there's an implication in terms of network resource consumption, and Disco is simple. It doesn't worry about that, but I think it would be nice to get Disco smarter about that so that it can scale across larger clusters. Now, one thing that often crops up, and for a valid reason, earlier was Disco was often compared with Hadoop, because at one time both were implementations of map and reduce. And it was possible to compare them and contrast them. I think that those days are over. And it would be good to know that when you try and compare Disco and Hadoop in the same sentence, what exactly are you comparing? Because the storage, HDFS and DDFS storage are completely different. So you can't really compare them very easily. And the Disco, I mean, Hadoop last year moved to a new model, which, new generation, I forget what it's called, yet another something. So they have a new compute model. The next version of Disco will have a pipeline compute model, which is kind of different. So in both the compute and storage aspects, Disco and Hadoop are diverging. And it would be, when people try and compare, it would be good to know that you're actually comparing apples and oranges. So that's where I'll kind of conclude. If you have any questions, I'll take them.
Thank you.
Thanks. Yep.
Can you give one or two examples that would benefit from the new computational models? You said it's more flexible than traditional MapReduce, other than locality issues.
Yeah. So if I have network access, there's. Let me try bringing up. So there's this company called Continuum.io, which is a Python company. Let me just bring up, they have a blog I'm trying to access. You know where the blog is? Yeah. So here, they use Disco in their sorry. I want to give you something that I'm not cooking up, so that it's a concrete example. I think it's.
Like if you are looking for the article about this, you will scroll down.
I'm not sure if it's this one. So on one of these articles actually discusses, he implements his computation as a sequence of Disco jobs. Okay, there's a sequence of MapReduce jobs. Some of them are map only, some of them are reduce only. So in order to do his computation, he had to write a sequence of like 3 or 4 Disco MapReduce jobs. And some of the stages were just map only and reduce only. So he was constrained to express his computation in terms of MapReduce. In this new pipeline model, all he has to do is have a single job with multiple stages. So that's it's flexible in that sense. You can. Yeah. Yep. Sorry?
Is the pipeline linear, or can you do branching?
So the question is whether the pipeline is linear. Yeah, that's one of the restrictions of the pipeline. It's a linear stage. Let me go back to this. So it is a linear sequence of stages, okay? But across subsequent stages, there is branching and joining going on. So I'm not sure in what context you mean by linear. So there's a linear sequence of stages. So each stage runs the same computation. So it is, I would call it a linear, it's a linear pipeline. But so you can't have a fork in your pipeline and a join currently. Like I said, I mean, if you look under the hood and if you're an advanced user, you can kind of use labels to implement forks and joins, but that's kind of you're really poking under the hood, and it's not nice to
have to do that. You could think of high-level tools like Pig that implement fork and join using labels. And so it's kind of abstracted away from the ordinary user. But I would say we don't have forks and joins.
Any other questions? Well, I have like one question. So
Sure.
have there been any updates to DDFS? I didn't actually remember what was the talk last year that you gave, but I mean,
Right.
there are a number of things that
Yeah, so last year, DDFS, in fact, last year, most of the work was done on DDFS. What we did was we implemented a new garbage collector. That was kind of motivated by fixing, there was a race condition in the garbage collector. And so it was kind of, to fix that race condition, we kind of redid the whole garbage collector. And while fixing that, we also added a new feature where you can allow nodes in the DDFS cluster to be scheduled for removal. So suppose you decide that you want to remove a certain node from a DDFS node from the cluster. Now, there's a lot of data sitting on that node, and you can't just remove it. Because it might have the only replica of a certain a data blob. And you would like that data blob to be replicated on other nodes in the cluster before you remove this node. So we have a new feature where you can mark that node to be mark that node for future removal, so that all existing data is migrated off that node. And you are given an explicit indication that it is safe to remove that node. So you don't have to guess and do a Hail Mary pass and then just remove a node and then just hope your data is actually replicated elsewhere. So you're actually given an indication when it's safe. So that was the DDFS stuff last year. So it's been around. It's in the existing stable release of Disco.
Right. And also, I remember you mentioning something about rack locality and like the improvements that could be made to the networking aspect.
That is, it would be, future work, yeah. I mean, we were looking into that, and we have some ideas on how to do that, but yeah.
Well, can you just say a word about like what's the problem there? So
yeah, so the problem there is that Disco's, it's a very intentionally very simple implementation of MapReduce, and it's the idea of the and one of the guiding goals of Disco is it should be dead simple to set up and configure. And when you configure your Disco cluster, all you just have to provide is the names of your nodes. You don't have to specify which nodes are local in one rack. That adds some configuration complexity. As a result of that, Disco's idea of your cluster layout is that all nodes are like equally distant from each other, which is not really the case in physical clusters and not true in virtual clusters either. But so one consequence of that is when you're shipping data across the network, Disco doesn't know whether it's shipping data from one server to another server that's in the same rack, or one server that's kind of across the cluster in a different rack. And there are efficiency implications for these two different transfers. And so it doesn't do the right thing in certain cases. It can, for a very large cluster, you have almost all the data going across the core switch, and your cluster will not perform well. So it would be nice to fix that, and we have some ideas on how to fix that. But that's the underlying issue. Yeah.
And actually, just another thing that like we have been actually actively collecting a list of companies who are using Disco. So if any of you have been using Disco or are considering to use Disco, I mean, like maybe kind of help Prashanth.
Yeah.
Since like we will be updating the website soon and so forth.
Right. So we have these companies, and if you're not on this list, that's because we don't know about. We haven't heard of you. So. Please join this elite club.
Thank you.
All right, thanks.